Okay, lesson 7, buoyancy. We're going to be talking about Archimedes' principle. We're going to try to understand it, and then we're going to apply it to buoyancy problems. I really like this lesson. There's an awful lot of problems that I have for this one. We're not going to get through them all, so I'm just going to kind of, I'm going to do the best I can. Because this lesson tends to run long, so I'll try not to get too wordy about other things. Unfortunately, I need to do an aside before we even begin. Because, having done a lot of hydrostatics, I want to make sure that there's one thing that kind of, I guess it throws people and when drawing free body diagrams and things like that. So what I want to do is I want to think about a column of water and why it stays where it does. Okay, so for example, and it doesn't have to be water, it could be any fluid. But let's imagine that here's the surface of some fluid, and I'm going to draw just a column of this water. Okay, I'm going to kind of give it dimension as best I can. Obviously, I'm not a perfect drawer. There you go. So here's a column of water. All right, and so the question I have for you for this column of water is, why doesn't it go up or down? Doesn't it rise or fall? Okay, so this is a static fluid, and for any column you might say, well, why doesn't it go up or down? And hopefully, you guys have been doing a lot of fluids here. I mean a lot of hydrostatics, and you've done a lot of statics and things like that. So hopefully, right off the bat, you're saying, oh, well, that's easy, right? Because the sum of the forces in the z equals 0, right? Because that's why things don't move. Okay, or that is a requirement for things not to move, or really for things not to accelerate. But certainly, in order for you not to move, you can't accelerate. So anyway, so that's cool. So anytime we want to analyze the sum of the forces in the z equals 0, we need to think about we need to do a free body diagram. Okay, so what I'm going to do is I'm going to draw a free body diagram of this column, which luckily is an easy free body diagram, or at least it's an easy drawing. So there it is. Okay, and I guess, if I was a better, what do you call it than I am, we could have it like that. Okay, so now what are the forces on this thing? Okay, well, we've got an atmospheric force on top, PATM. Okay, what's going on the bottom? Okay, so that's going to be multiplied times the area of this thing. And let's suppose this has units of delta x, delta y. This is h. Okay, so this atmospheric pressure is creating a force, PATM, times delta x, delta y. Okay, so that's the pressure times the area, pushing down. And then what's pushing up on the bottom? Well, whatever the pressure is at the bottom. Okay, let's call that, I don't know, just P, I guess, or P bot. Okay, P bottom. We'll just write it all out. Times delta x, delta y. Okay, what other forces am I missing? What am I missing? What am I missing, you punk? All right, you know it. We're missing weight. All right, so I've got a weight somewhere in here, and I'm going to push it down like that. Okay, so this is going to be the weight. Okay, what's the weight? Well, in fluid mechanics, the weight is the specific weight times the volume. Okay, if you prefer rho GV, if you prefer. Okay, so those are all of our forces. If it were moving, there would actually be a viscosity, there'd be like some shear stress on the walls, but it's not moving, so there's no shear stress. All right, so let's do it, shall we? All right, so the upward force is P bottom times delta x, delta y, delta x, delta y. Okay, you know how it is, delta x, delta y. Okay, minus the weight. Or let's see, minus PATM, delta x, delta y. Okay, minus the weight, which is gamma. And what's the volume of a prismatic solid? It's going to be delta x, delta y, h. Delta x, delta y, h equals 0. Okay, cool. So one of the nice things about this, and this is one of my favorite quick derivations here, is that delta x, delta y are on every term, so they go away. It kind of makes sense that they would. The pressure atmospheric, what I'm going to do is I'm going to make this 0, which means I'm working in gauge pressure for the rest of the problem. Okay? And then if I rearrange this sucker, let's see what we get here. P bottom equals gamma H. Whoa! Did you see that coming? Did you see that coming? Okay. If I had asked you a second ago, what is the pressure at the bottom of this thing, what would you have said? Okay, well, you said, well, you hopefully would have said, well, it's hydrostatic. It has a constant density. Okay, so now I want to take that a step further, a slight further, and I want to think about this. Okay, so this is the hydrostatic law, essentially. This was a quick derivation of it. But there's something else here, and that is this, okay, and this is important. Okay, if I just looked at a sliver of this fluid, so thin that it has no weight, okay, because it's so thin that it has no weight, and I said, what is the because so thin, right? That's impossible, but whatever. Okay, so I said, what is the force balance on this little sliver? Well, you might say, okay, well, there's a pressure on the bottom, okay, and it's a hydrostatic fluid, so that pressure is gamma times H. And then you might say, oh, but there's a pressure on the top, okay? And it's so thin that the H is the same in both of these, so that's gamma H as well. But then you might also say, well, look, but here's the thing. Well, those are pressures, right? So the pressures need to be multiplied times the area of that sliver. Okay, but then you might also say, well, what about the weight? There's also a weight of water on top of this thing, the weight. Okay, so essentially the top of this thing is, hydrostatic. The bottom of this thing is hydrostatic, but this thing is also supporting the weight of the fluid. Okay, and what I want to tell you is this. If you do this, you have double count. Okay, I think hopefully you can see already that this is not going to work, right? Because this weight plus gamma HA is greater than the gamma HA, so this could not be hydrostatic. And so the weight of the fluid above this sliver is what causes this pressure. Okay, so if you use both of these, you are double counting. Okay, so this is double counting. Double counting. Okay, so when doing a free body diagram of a fluid, okay, the weight above equals the pressure on the top face. Okay, so don't double count. Okay, now it's different if we're talking about, like, for example, if I gave a sliver that looked like this, okay, and I said, well, what's going on with this one? Well, on the top face, I could do the weight of the water above it, or the hydrostatic force, which would be gamma HA, okay, where H is from here to the surface. Okay, let's call this delta H. Okay, and then underneath it, this would be gamma H plus delta H times A. Right, and then there would be the weight of this fluid itself, weight of the fluid in the block. Okay, that would be different. Okay, and if you solve this, weight is going to be gamma delta H A. Okay, if you solve that equation, which of course makes sense. This is gamma times the volume, gamma volume. Okay, if you solve this free body diagram. Okay, so just something to just keep in mind. Okay, so up here, it either has to be the pressure as I've done it, or it could be the weight of this fluid, which ultimately, if you do, it's going to be gamma times the volume, which is H times A. Okay, so it's one or the other, and they end up being the same. Okay, so I recommend, I usually just use the pressure. Okay, so that's an important point. Okay, that just kind of gets lost in all this stuff, and I think when I learned all this, I didn't learn that. I just kind of, I internalized that eventually, but no one ever said anything to me. All right, so now we're going to talk about buoyancy, and I want to talk about the buoyant force. And I'm going to take a second. Well, it just isn't going to take all that long. So here's the buoyant, and I'm going to put the word force in quotes. and you'll understand why in a second, because I don't think the buoyant force is really a force. So here we go. Okay, and this also goes back to not double counting. All right, so in 3D, I'm going to look at, just like I did a second ago, a block of fluid. Okay, but what I'm going to do is I'm going to give it dimension in this direction. Okay, we'll call that dimension delta y, this dimension is delta x. That's how I like to do things. And I'm going to call this, I don't know, delta h, and we'll call this distance here to the surface h. Okay, so there's a, the surface, kind of does that. Okay, so, and this can kind of go up to there, and there's an imaginary kind of top up there. All right, cool. So again, why is it, in this case, I'm not actually talking about a fluid. This is just something. Okay, so this is not a fluid. This is something. Okay, it could be, a block of fluid, but it could also be something else. It could be, a weight, or it could be a balloon, or it could be anything. All right, so what I want to do here is I want to think about the forces on this something that's underwater. Okay, and so what we're going to do is, well, the forces on this thing are, well, we've got a weight on it, whatever its weight is, weight. Okay, and we've got a pressure on it. And let me see if I can draw that in a different color. Maybe it'll show up a little bit better. But the pressure on the top, which already you should be thinking you know what that pressure is. You know what this pressure is. What's that pressure? Okay, that's right. It's gamma times h. Okay, and there's a pressure on the bottom. Okay, so already you should be thinking that you know what that pressure is. Probably your mind wants to say that it's gamma h, but in this case it's not gamma h because it's gamma h plus delta h because we're a little bit deeper. So the pressure on the bottom, okay, or the force on the bottom from the pressure, okay, let's call it force bottom vertical, equals, let's see, gamma. So it's going to equal the pressure on the bottom times area of the bottom, delta x, delta y. Okay, what's the pressure on the bottom? It's going to be gamma h, but it's not really h in this case because we're deeper than that, h plus delta h. Okay, times delta x, delta y. Now, note real quick that this gamma, we're talking about the gamma of this fluid out here. Okay, that's really important. That's the most confusing thing about this whole thing. Okay, and then on the top here, and it's going to be, I'm going to kind of label it over here, we've got the force on the top in the vertical, and it equals, well, let's see, it's gamma times the depth. So that's gamma times h, that's the pressure, times delta x, delta y. So that's pressure times the area. Cool, right? All right, now on the sides here, we've got like that and like this. Okay, that's a little bit too big, so we'll delete that in there. Okay, so it's hydrostatic, so it's increasing linearly with depth. Boom, right? Now I'm not going to, so this would be F, I guess, left side horizontal force. Okay, I'm not going to spend any time on that because I don't want to draw the right-hand side, but on the right hand, there's an equal and opposite force to that. So we're not really too worried about that, right? Those are just squeezing our something. Okay, something is getting squeezed. Okay, those two are not causing it to want to go up or down. So what I want to do is I just want to think about this top force and this bottom force. Okay, so what we're going to do is I want to think about the bottom force and the top force. I'm going to ignore weight for now. Okay, so this exists, but we're ignoring it for now. Okay, so what I've got is I've got Ft in the V, that's a negative force, plus F B in the V, okay, those are my vertical forces, equals negative gamma h delta x delta y plus gamma h plus delta h delta x delta y. Cool. All right. So this, well, let's just kind of clean up this this right-hand side here. So I'm going to pull the gamma out. Let's see, what else can we pull out? Delta x, delta y, delta x, delta y can be pulled out. And I'm left with negative h plus delta h, okay, equals gamma times delta x, delta y, delta h. Okay, equals gamma, what is this? Delta y, delta x, delta y, delta h. Hopefully you can see it. That is the volume in this case. So this is the volume. Okay. But I want to make two things clear here, okay? So basically this right here, so right here, I'm going to write this as difference in pressure forces on top and bottom, okay? This is called the force of buoyancy. That's how we define the force of buoyancy. It is the difference of the pressure forces between the top and bottom. Okay, that is the force of buoyancy. Okay, and that's why I call it force of buoyancy, you know, the buoyancy force, and put it in quotes, because it's not really its own force. It's actually just the difference of two other forces. Okay, so that's really, really, really key. Okay, now what I want to make note of, and there's a lot of different ways to do this, is force of buoyancy equals gamma. This is the gamma of the fluid that surrounds the something. It has nothing to do with the specific weight of the something or the density of the something. It only has to do with the fluid that surrounds the something. Okay, so that's all out here. Okay, this volume right here, this is what we're going to call the volume displaced. Okay, and this is really, really important. So you see where delta x, delta y, and delta h are. Okay, well, if this derivation, if instead I had derived it like this. Okay, so we're imagining we're, you know, at the surface or something, and this something is floating. Okay, then we have to imagine that, okay, so like that. Okay, hard to draw, right? Because, you know, I'm not a genius at this, but hopefully you can kind of tell what I'm driving at. So if this thing were floating, then notice that this volume displaced is this volume right here and does not include what's above. Okay, so that is the volume displaced. So the volume displaced is the volume that would have fluid, but it doesn't because the object is there. Okay, and this is critically important right here, those things. Okay, or in Archimedes' way of thinking, okay, is the weight, this is the weight of the displaced fluid. Okay, and I'll have a, I'll post a link to a YouTube video where a guy kind of proves that. It's pretty quick. You know, the guy's obviously a good teacher, but he's just, you know, it just doesn't take him very long. Okay, so force of buoyancy, weight of the displaced fluid, and you can see that kind of from this. Okay, so if I went back to this fluid right here and I wanted to know how much does it weigh, well, I would say, oh, well, the weight of that is gamma. Okay, if there were fluid, right? So it's the fluid that would be there. It would be the gamma of the fluid times the volume of that box, okay, which in this case is the volume displaced. Okay, so that is how, or in this case, it would be if I said, what's the weight of the fluid here? Well, we need to find the volume of that box, okay, which is in white, and we multiply it times the gamma, so of the fluid around it that's not there. Okay, so that's how we do it. Now, some of you might be saying, okay, well, cool. Okay, so this is the definition. Let's see. Okay, this force right here. Okay, it acts at the center of buoyancy. Buoyancy. Okay, which I have written as doyancy because. You know, this is an advanced class, and so anyway, so what we typically do in a problem, so you notice I ignored the weight a while back. So typically what you do with any sort of one of these problems, is that you're basically, so here's the weight, okay, and it equals the gamma of the object times the volume of the object. Okay, note that in the case of something being submerged like this, okay, the volume of the object is the same as the volume displaced. Okay, in the case of it floating, the volume of the object is this whole thing. Okay, and that makes perfect sense, right? The weight, okay, is not affected by whether or not by floating or not, or anything to do with, or anything to do with location. Okay, I mean, unless you like go up to the top of Everest or something and your gravity gets slightly less or whatever, but you know, we're not dealing with that in this class. So what you need to be careful with is if you look at these two formulas, they're very similar. Okay, and typically what we do in these problems, I say typically, like almost always, is you go and you say, okay, well, here's my free body diagram of my thing. Okay, there's a buoyancy force going up and a weight going down. Okay, so this is just a random free body diagram. Okay, now be careful here. One last thing. This weight acts at center of gravity, or center of mass, or you know, whatever. All right. So anyway, so this is our free body diagram. Now remember, once we have this buoyancy force, we're not going to draw the pressure on top or the pressure on bottom. That would be double counting. Those are included in this buoyancy force. Okay, so do not do both. Okay, so once we have this, we say, oh, okay, well, here's my problem. Sum of forces into z equals 0. Force of buoyancy minus the weight equals 0. And then we go and we say, okay, well, that's gamma of the fluid times the volume displaced minus the weight, which is the gamma of the object, times the volume of the object equals 0. Okay, so this is very commonly how we do it. Okay, you could almost like copy and paste this because this is going to be the way we work a lot of these problems. Now, if the thing is submerged, then these two are equal. If the thing that, you know, we drew a free body diagram has the same density as that of the surrounding fluid, then those two gammas are the same. If, you know, so, but they aren't always the same. Usually the gammas are not the same. The volumes can be the same fairly frequently if something is submerged. All right, so before I get into working a bunch of problems, okay, we're 23 minutes in, so we're doing okay. But I want to talk about, before I start working problems, I want to talk about stability. Okay, and if you are a naval engineer, this is going to be really, really, really important to you. Yeah, so we'll do a few things here. First, if, and this is kind of obvious, if the force of buoyancy is greater than the weight, then the object will rise. Okay, if the force of buoyancy equals the weight, then the object will stay where it is. Okay, and if the force of buoyancy is less than the weight, then this object will sink. Okay? Now, if we are talking about an immersed body, okay, so this is just kind of like a body that is floating or sitting on, so we imagine, so there's kind of like a standard thing. So we imagine, for example, in this case, it has to do with where the force of buoyancy and where the weight act. Okay, so if I imagine an object like this, okay, and it's kind of got, kind of more mass kind of centered towards the bottom. Okay, then what ends up happening in this case is we end up with, okay, so, well, here, let me do the neutral case here. Okay, where the mass is kind of evenly distributed everywhere. Well, then what I can do is I can say, okay, well, here's the weight. It's going downwards, okay, because that's the center of gravity. The center of buoyancy in a case like this, well, it's the same too. Okay, so the force of buoyancy goes like that. Okay, this is what we call neutral. This is just a neutral body or whatever. And then this one I'm going to call stable. And what's happening here is, so the center of buoyancy just has to do with the displaced fluid, so it remains right in the center of this sucker. Okay, so the force of buoyancy. Okay, so it is in the center. Okay, so the center of buoyancy. Okay, and this only comes from the displaced fluid, the displaced volume. Okay, so however, if we were to do the center of mass, it's going to have shifted down a little bit. It's going to be like down here. So this is the center, sorry, that's the, well, that dot is the center of mass, but this is the weight. Okay, so we'll turn that into a W. Okay, this is stable because if something were to happen here, right? So if something were to roll this thing, okay, you imagine, I don't know if there were those little, when I was a kid, they had little toys that worked like this, and you could knock the toy over and it would roll back up and it would fix itself. And the reason it fixes itself is because if this thing were to roll, so I'm going to imagine this thing taking like a little turn this way, somebody pushes it or whatever. And so now it's rolled over here a little bit, right? And so when it rolled, this mass is now like this. Okay, the center of buoyancy is still kind of like right here. Okay, force of buoyancy is right here. And the center of gravity is right here, so here's the weight. Okay, can you see the effect that this has on the, like what kind of moment we get out of this? Well, the moment is trying to turn this way. Okay, so this is restoring. Okay, so that's really important. So that's why this is considered stable. Okay, similarly, we could imagine the same sort of thing, or for the unstable case, okay, where for whatever reason, somebody put the weight on the top. Okay, now the force of buoyancy is coming from the center of buoyancy, which only has to do with the displaced fluid, and it should be right in line, is the weight. Okay, it's all fine and good until somebody tips it, right? And once somebody tips it, okay, so somebody tipped it this way. So now the weight is over here, and the center of gravity is here. Force of buoyancy remains where it was. Okay, and the net effect of that is, I don't know what the opposite of restoring is. It's just unstable, right? So if you look at that, right, it's going to kind of, they're going to reinforce each other. So it's going to reinforce the push. Okay, so this, and I think you can imagine this is going to roll. Okay, so this is really important, and this is what happens in ships. Okay, so we could imagine, it gets more complicated as you start thinking about like a boat, but I'm going to draw a boat. So we imagine a boat. That's my boat. Sorry, that was Forrest Gump. If you guys haven't seen it, I'm making fun of Forrest, although I like Forrest. Okay, so we imagine, in this case, you've got a boat. Okay, well, what happens when you tip that boat? Well, okay, first, initially, okay, the force of buoyancy is right in the middle. Force of buoyancy is right in the middle, and maybe the weight's a little bit up, right? Like, let's suppose this thing is a little bit top heavy, right? So you've got, I don't know, let's suppose you got a little bit of weight right up there, okay, because you put your weight on the top. Okay, so here's the weight. So basically my point is, for the boat, basically, is that this is going to be a little bit more complicated. Okay, so what's going to happen here is when you tip this thing, so for whatever reason, it gets tipped a little bit, so a torque is applied because, I don't know, somebody jumps on the boat or, whatever. Well, what's going to happen is this thing is going to start to lean. Okay, so I'm going to do my best to draw a leaning boat. Okay, not a tower, but a boat. Okay, so here we go. Okay, now, this boat, okay, I might have overdone it. But what happens is the weight kind of is going to stay kind of where it is, okay, like this. Okay, but what's going to happen, at least initially, is that the buoyancy has to do with this. Let's see if I can do this in like a different color. Okay, so here's the submerged volume. And so if you want to look for the center of that volume, okay, that's where the force of buoyancy is. So at first, you know, the center of buoyancy is actually going to move to the right because you can see that there's more volume displaced over here. So the force of buoyancy is going to be here. Okay, so this will be stable. Okay, because this is going to resist that push, right? But then if for whatever reason the initial push here, okay, if whatever caused this thing, suppose this were a downward force, if it was large, say, okay, then okay, so if the force is large enough, then what will happen is this thing will tilt to the side enough. Oh, I don't want to do that in red. Let's do this, and let's do white. And so suddenly your boat will get far enough over. Okay. I mean, obviously I'm exaggerating this, and each boat is going to have its own characteristics, but the force of buoyancy will be here, and the weight will be here. Okay, and again, the force of buoyancy only has to do with the submerged bit. Okay, but it's not enough for the weight, and in this case, it's going to go all the way over. Okay, so this will be unstable. Okay, so boats are more complicated because the force of buoyancy is going to move, and it's moving essentially because this thing is, well, first of all, because it's, you know, as it rotates, the volume that is displaced, it has a shape. Okay, and that shape matters for where the center of buoyancy is. We're not going to do anything with this. It's just something that I think is important to kind of mention. There really just isn't enough time for me to do this in this course. We could come back to it. In the end, if we have time and I say, you know, do you guys want to do some special topics, and anybody wants to talk about this, we can work some problems on this. Okay. Anyway, I want to start working some examples. We're 30 minutes in, so it's time to kind of get into that. But I think this stuff is pretty fascinating. Just something to kind of be aware of. So what I want to do as we work through these problems is I want you to keep this in mind right here. Let's see if I can actually grab this. I can't grab just that little bit. Okay, but I want you to keep this in mind because I'm going to probably end up drawing this or talking about this on every single problem. Okay, so wherever you have that in your notes, you know, highlight it, bring it with you, whatever. And we're just going to work a bunch of these, okay? So let's, some of these are kind of academic. They're not the sort of problems you would have on a test. It's just to kind of make points that come out of the math. But let's start. Okay, this is going to be example number 1. Example 1. All right, so here we go. Okay, and we've got some kind of scale here. So they love drawing scales like this. Okay, and now on the bottom of this thing, there's a 50-pound something. I think the way I wrote it was that this was a boulder. Doesn't have to be a boulder. In fact, 50 pounds doesn't really seem like a boulder. Maybe a little baby boulder. What do y'all think about that? I think boulders are almost like fundamentally not babies. All right, so anyway, it's lowered into the ocean or the river or whatever it might be. And so the question is, what does the scale read? Okay. And actually, we could actually pretty well get at this if I knew the volume of the boulder. Okay, I don't know the volume of the boulder. But the question is, so we have two questions. That one, and does the depth matter to the reading? Okay. Okay, so this is going to be given. This is going to be required. Okay. And anyway, so let's see. Solution. Well, let's see. This thing is, this is sum of forces in the z equals 0. I think we can all agree with that, which means, well, let's see. Oh, there's a sum of forces. That means there needs to be a free body diagram. Luckily, this is an easy one. Okay, 50 pounds. Okay, going up, so that's the weight. We've got the force of buoyancy going up, and we've got the tension. Okay, so I'm just going to switch to which two of those are. Okay, so tension and force of buoyancy going up. All right, so the tension plus the force of buoyancy minus 50 pounds equals 0. All right. Well, let's give this sucker a. Should we give it a volume? We could give it a volume. Let's give it a volume. Okay. Let's make the volume small. Let's say the volume is I don't know, 0.1 cubic feet. Okay. Hopefully that doesn't screw up the problem, but it might. Okay. So what we're going to do here is we're going to say the tension. What's the force of buoyancy? Well, that's gamma of the fluid. Okay, times the volume displaced minus 50 pounds equals 0. All right, so the volume displaced, is that the volume of the whole rock, or is that just part of the rock? Okay, hopefully you're seeing that the volume displaced is the volume that would have fluid if the object was not there. So if this rock were to magically disappear, fluid would fill that entire volume, right? So that whole thing is the volume displaced. So we're going to go with 0.1 feet cubed right here. Okay, the gamma of water, okay, is 62.4 pounds per cubic foot. The tension is here, and minus 50 feet equals 0. Okay, so let's solve for this, and we end up with 43.760 pounds, okay, or 43.8 pounds is what we would report. T equals 43.8 pounds. Okay, pretty good. All right, so notice it was lessened, okay, because the force of buoyancy is basically supporting some of that weight. I want to note here too something, because this tends to throw people off. Okay, the weight here, notice I never used gamma of the object times volume of the object. Why didn't I do that? Because it gave me the weight. There was no reason to expand to that. Okay? Now, the second question here is, does the depth matter? Okay, if I go deeper, okay, does the depth matter? And usually I ask my class this, and a lot of times we don't get this right. Okay, and some people think the depth matters, some people think the depth does not matter. And I'll tell you right now, did you see anything in here about depth in any of this problem? No. Depth does not matter. And I'll tell you why, okay? And it's because, remember, the force of buoyancy is the difference in the pressure on the top and the bottom. If I am really shallow, okay, the pressure force on the top looks like this, pressure on the bottom looks like this, right? It's a little bit higher. Right? If I'm really, 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 really deep, okay, let's imagine I'm here. Okay, the pressure on the top has increased by a bunch, because I'm a lot deeper, but the pressure on the bottom is increased by the same amount. Okay, and it is the difference in these two pressures that matters, not their absolute amount. Okay, so the difference in the two stays the same. Okay, and that difference is only defined by the difference in depth between the top and the bottom, okay, which is the same no matter what. Okay, and you can go back over here to our initial derivation where we did that, and you'll see that, let's see, where did we do that? Oh, it's over here somewhere. But yeah, so the key thing is right here, that delta H was all that mattered. Okay, so when we got to the end over here, it was delta H. Okay, so it has nothing to do with the depth, it only has to do with the difference between the top and the bottom. Okay, so that's that. By the way, bear with me, this is difficult stuff, okay? So let's not underestimate what we're looking at here. Okay? All right, example 2. All right, and this one's pretty hard. So I'm going to pause it and write it out. Okay, so we've got two comparable situations. So we've got a tank of volume V that is full of water, gamma W, and then in the next section, I've put a ship in there. So by putting the ship into the water, some of the water kind of flowed over the top, okay, but the tank is completely full. It's the same tank. So this is fairly complicated because we're thinking about weights here. By the way, just to let you know, the point of all of these examples is to get you thinking about the difference between the volume and the volume displaced, and the gamma of the fluid, and the gamma or the or whatever's driving the weight of the object. Okay, so that's the point of all of this. Okay, so So, and this one is no different. Okay, so what is the weight of the left-hand situation? Well, it's just the weight of the water. Okay, so what's the weight of the water? Well, in fluids class, we do that by doing the gamma of the water times the volume of the water. Okay, so, all right, done. Okay, whew, that was hard. All right, now let's do the left-hand side, or the right-hand side. Okay, so on the right, we've got the weight equals, well, there's two things. And so one is the weight of the water plus the weight of the ship. All right? Okay, so we want to add these two things up. Okay, so, well, the weight of the water is it's a little bit different here. So it's not the total volume of the tank like it was in the last one. Let's, instead of calling this the weight of the water over here, the volume of the water, let's call that the volume of the tank. Okay, because that... Okay, so, so we're going to call it the volume of the tank, right? So here we've got the weight of the water is the gamma of the water times its volume, which is going to be, but there's less total water, right? So it's going to be the volume of the tank minus whatever this little volume right here is, okay? Because that no longer has water in it, okay? What do we call that? Call that the volume displaced, right? Okay, so that would have water in there if the boat weren't there. Okay, so that's the volume displaced. Okay? Now, the ship. Okay, what is the weight of the ship? Well, that's kind of hard to get at. Okay, so we're going to do a little aside over here to get at that. Okay, and what I'm going to do is I'm going to do a little free body diagram of the ship. The ship's not moving, right? It's not going up or down, so that means we've got a force of buoyancy, and we've got the weight. Oh, look, right there. There's a way for us to get at the weight of the ship. Okay, so the sum of the forces in the z equals 0. So that means the force of the buoyancy minus the weight equals 0, which means the weight equals the force of buoyancy. Oh, this is good. Oh, I guess that's weight of the ship, right? To stay consistent. Okay, so the weight of the ship equals, what's the force of buoyancy of the ship? Okay, well, the force of buoyancy has an equation, and it's the gamma of the fluid that surrounds it, so it's the gamma of the water, okay, times the volume displaced. Okay, the volume displaced. Okay, so I can plug this as the weight of the ship in for this weight of the ship right here. Okay, so it's going to go right here. Gamma of water times the volume displaced. Okay, so the weight equals, well, if we distribute this gamma weight, then we'll see that the gamma W volume displaced cancels, and we get gamma water volume tank. Okay, so now we're ready to compare, and look at that, they're the same. Don't you hate these trick questions? Okay, if somebody asks you what weighs more, A or B, okay, almost always the answer is they're the same. Somebody says, which one of these lines is the longest? Well, and you're like, well, I know there's an optical illusion. They're going to be the same. Okay, which kind of sucks. It makes it less fun once you realize that. But what do you do? Okay, what do you do? Well, I know what you do. You student. I teach. Anyway, hopefully my goofy laughing doesn't aggravate you all. All right. All right, so on this problem, we have two fluids. Okay, so we've got water on top of mercury, so that's gamma water over gamma Hg. Gamma water, gamma Hg. Okay, and by the way, you'll notice that mercury is the favorite fluid to use in fluids besides water because it has the highest specific gravity. And we've got some block kind of just floating in these two liquids on their interface. Okay, and it's got a specific gravity of 7.85. So obviously water has a specific gravity of 1, mercury has a specific gravity of 13.6. So somewhere in between, this thing is going to float. Okay, and so what we want to know is so this is given, and we want to know is what is the ratio of A over B. Okay, so mathematically this is a little bit annoying, but it's really important that you're able to get the concepts here. Okay, so the solution Okay, well, we're going to deal with the sum of the forces in z equals 0, as we almost always will in a what do you call it, problem. The only time you won't do that is sometimes sometimes the question will be, does something float? You know, if I submerge a basketball, does it float to the top? Well, what you do is you imagine it submerged, and then you just add the forces, and they don't equal 0. You're just going to check to see if the forces are positive or negative. If it ends up being positive, then it floats, negative, then it sinks. Okay, so that's, you know, but you're always summing forces in buoyancy problems. Okay, so if we're going to do that, then we're going to need a free body diagram. Okay. Oh, I'll note this has a horizontal components of L and a width of W. So that width is into the page. Okay, so what we're going to do is I'm going to draw a free body diagram, and this will happen to you sometimes, and this is a little bit annoying, but it will happen. And what I want to note is that, how many weights does this thing have? Well, it's just a block of some material, so it's got one weight, okay, and the weight acts like right here. Here's the weight. Okay, how many buoyancy forces does it have? Well, in a technical sense, it only has one, because really there's only one pressure on the top and one pressure on the bottom. But those pressures are kind of hard to get at, so we're not actually going to do the pressure. So I could, as an alternative to this, I could calculate pressure on the top. What's the pressure on the top again? Oh yeah, it's gamma H. Remember that? Yeah, it's gamma H. Okay, that shows up a lot. Okay, and I could do the pressure on the bottom, which would be a little bit larger. Okay, I could do that. Okay, what's the pressure on the bottom? Is it gamma H? No, it's not gamma H, and that's really annoying. Okay, why isn't it gamma H? Well, because there's two fluids of different gammas above it. Okay, so the way you could get the pressure on the bottom, if you wanted to, okay, so the pressure on the top would be gamma water times H. Well, whatever H is, so that would be this H right here. Okay, the pressure on the bottom would be, well, we would need to figure out what the pressure of water is right at this point right here. So that would be gamma water, and that depth would be H plus A. Okay, and then I would have to add the gamma of mercury times B. Okay, so I would add, so basically from this point on, I would add whatever it takes to get to there. Okay, this would be just like a manometer, essentially. But we're not going to do it that way. Okay, you could do it that way. Maybe we'll hold on to that and do it again. But instead, we're going to do this. We're going to do this using, because I don't want to do that. Okay, so what we're going to do is we're going to do it this way. Okay, here's our object. Here's our weight. And I've got the buoyancy due to the top liquid. Well, technically it's like right there, but F buoyancy due to water. And then I've got another force of buoyancy due to mercury. Okay, so I've got two forces of buoyancy. Okay, and that's interesting. Okay, so just to zoom in so you can really see that. Okay, and we're going to go over here, and I'm going to say, okay, well let's do this. Okay, so I've got force of buoyancy due to water plus the force of buoyancy due to mercury minus the weight equals 0. Okay, now we have to think about what goes into these places. Okay, so the force of buoyancy due to water. Well, that's going to be the gamma of the water. Okay, remember this all buoyancy has to do with the fluid displaced. It has nothing to do with the object. Okay, the gamma of the water times the volume of water displaced. Water displaced. Okay, plus the force of buoyancy due to mercury. So that's the gamma of mercury times the volume of mercury displaced. Okay? And then minus the weight. Now the weight has nothing to do with the fluid, right? So that is the gamma of the object times the volume of the object equals 0. Now before we continue with this, you should pause and make sure you understand what all of these things are going to be. Now I'm going to talk about them as we go, okay, but you need to make sure that you understand why I chose those things, okay? So then we know the gamma of water, and we should know, well, let's just go ahead and plug some things in. Okay, so the gamma of water, the volume of the water displaced. Well, if we go to our original diagram, okay, that's this area, that's this volume right here. Okay, so the whole point of this problem is to make you think about what the volume displaced is. So the volume of water displaced is going to be A times L times W, okay, plus gamma Hg. Well, that's going to be SHG times the gamma of water, okay, times the volume of Hg displaced. Okay, so that's going to be BLW minus the gamma of the water. Okay, let's move that over there. I love it when that actually works. The gamma of the object. So that's going to be S of the object, okay, times the gamma of water, times the volume of the object, which is going to be A plus B times L times W. Okay, and let's move this, let's say right there. Okay, equals 0. Okay, and perhaps predictably, you might have imagined that this was going to happen. The length and the width of this object do not matter. Okay, they all cancel out. Okay, what else cancels out? Well, the gamma of water cancels out. Okay, so what shows you is that it's not the absolute magnitude of the water, of the thing that matters. It's the ratio of the specific gravities. All right? So let's write this as A plus SHGB minus S object times A plus B equals 0. Okay, I'm just going to call that S because that's what we called it up here. We just called it S right here. But note that that is the S of the object. So I'm just going to start calling it S because I don't feel like writing S obj each time. Okay, so we end up with A plus SHGB minus SA minus SB equals 0. So we're going to collect like terms. I'm just going to write it all out, and you can pause it and copy it if you want, but this is just algebra. All right, so if you do the algebra, you can pause it and kind of like, click through it and make sure that it makes sense to you. 0.839, okay, so 83%, okay, is in the mercury. Wait, is that right? A over B? No, 83% is in the water. Okay, so it's floating really high. Okay, note that this is all about the ratio of these specific weights. Okay, or excuse me, specific gravities or specific weights, whichever one you want. But note that this one right here, that really is the S of water, which is defined as 1. Okay, so it's really just, this is all about specific gravity, so the ratio of the densities. Okay, so here we are. We're not even to an hour yet, so we have time. So we can do this last beastly one. Although, you know what? Actually, let's see what would happen if we solved it with this free body diagram. Okay, so let's zoom in and let's just do that real quick. Okay, so you could have done it this way, and we would have ended up with almost the exact same problem. Okay, so let's do it. So sum of the forces in the Z equals 0. Okay. So we should note that these pressures. So we're gonna have the bottom pressure, which is gamma WH plus A plus gamma HG times B. Okay, that's a pressure. So it needs to be multiplied by the length times the width to get the force. Okay, so that's the pressure on the bottom. The pressure on the top, that's gamma water H times. Okay, so that's the pressure times LW. Okay, and now we're going to subtract out the weight, which is no different in this formulation, which is going to be gamma water times length times width. No, it's not gamma water, it's gamma the object. Thank you. Okay, important error. Okay, remember the weight has nothing to do with the fluid. Okay, gamma of the object. Okay, length times width times A plus B equals 0. Okay, and notice right off the bat, my length times my width, okay, goes away because they all have it. All right, so rewriting the next row, and we're gonna distribute. So I'm gonna have gamma water times A plus S mercury times the gamma of water, noting I'm just kind of expanding that, times B minus gamma water times H minus the gamma of the object. So that's going to be the S of the object times the gamma of water. A plus B equals 0. And we'll notice that these gamma waters are going to go away wherever they are, because every single term has a gamma water. So we're going to get H plus A plus SHGB minus H, okay, minus SA minus SB equals 0. Okay, noting that the H's now go away. And I think at this point, A plus SHGB minus SA minus SB equals 0. I think this is algebraically equivalent to what we had. Yeah, so this is equivalent to this. Okay, so no need to finish it. Notice you could have done this either way. Okay, so pretty cool. All right, so let's do the last problem, and it's going to take me a little time to draw this. So I'll pause it, and then it'll pop up. All right, so this is unquestionably a difficult problem. I would love to give you a problem like this on a test. I probably never will. It's a little bit, well, actually, you know, there's very good reasons why I never will. And actually, you guys could overcome those this semester because you have access to the internet. But anyway, so there's a wooden beam here, and so I'm going to kind of talk you through it. So this is a wooden beam, and so for whatever reason, this particular wooden beam is hinged at this point A, okay, to a wall. And most of the, or maybe not most, but some very large portion of this beam is underwater. Okay, it's just kind of sitting there. And what you can imagine is some of it's going to sit in water and some of it is not, and it's going to make an angle with the water, theta. And you can kind of imagine that, like, if you walk up to this thing and you were to push it in this direction, right, what's going to happen is, as you push it in that direction, more of the beam is going to go underwater. And as more of the beam goes underwater, the buoyancy force will increase, such that when you remove the force, it'll swing back up to being at angle theta. Okay. On the other hand, if you were to push it this way, then less of the beam would be underwater, and as less of the beam goes underwater, the buoyancy force would decrease. Okay, such that when you remove this force, it's going to drop back down to where it was. Okay, so there's a certain theta where this thing is just going to sit. Okay, so this wooden beam has dimensions of 15 centimeters by 15 centimeters by 4 meters in the long way. Okay, and it has a specific gravity of 0.6. Okay, so this is really kind of complicated business. And so obviously we're going to want to do some of the forces in, the sum of the forces in some direction, or really what might make even more sense is we might want the sum of the moments. Okay, but regardless of what we're going to want to do here, we're clearly going to want to be doing some summing, so that means we need a free body diagram. Luckily, I've already begun on that. Okay, so we're going to go up here. Okay, and you're just going to have to remember the picture. Maybe I can bring it with or something and just kind of make it small so that it's, not in the way or something. So let's just kind of put it right there. And then let's zoom in. Okay, so now we've got a drawing, and I've got a free body diagram. Okay, so at that hinge, we have two forces, AX and AY. And then I've got a weight, which is acting downwards. Now, where is the weight acting? Okay, hopefully, the weight is acting at the center of mass. Where's the center of mass of something that's 4 meters long? Well, it's going to be 2 meters down, from its endpoint. So let's go like this, and let's go like this. And we're going to call this 2 meters. Okay, so that's where the weight is acting. Okay, what about this force of buoyancy? Well, it's not acting. It doesn't, it only concerns the water that is, the portion of it that's underwater. So let's suppose the water is hitting, I don't know, like right here. Okay, we're ignoring the fact that, this thing has some dimension in this direction. I'm not going to deal with the fact that it's actually like that. I'm just going to pretend that it's like this. Okay, so this force of buoyancy is going to act at the center of what is submerged. Okay, so let's call the submerged length from here to here, let's call that L. Okay, and then that means that this is going to be acting at, I guess it's going to be L over 2. And this is going to be L over 2. Obviously, my drawing could use some work. Okay, and what's left right here, this is going to be 4 minus L to go from here to there. Okay, pretty challenging, right? There's a lot of lengths going on here. Okay, so what we want to do is I want to drive at these forces, okay? And really what I want to solve for here is I want to solve for L, right? Because if I have L, okay, where is L? L is right here. Okay, so this is L right here. Okay, so if I have L, that's really helpful. Okay. Okay, and the reason that I want L, if I zoom way in up here, is because I got a nice little right triangle right here. Okay, with this side of this triangle from here to here being 4 minus L, this side being 1 meter, okay, and this is the angle we want. Okay, so once I have L, I can say, oh, well, the sine of theta equals, equals 1 meter, the opposite over the hypotenuse, 4 minus L, right? And so if I can plug in for L, I can solve for this, okay? So that's the end game, that's the goal, okay? So, end game, Thanos snapping his, what a jerk. Anyway, all right, so let's do this, okay? So what we have to do here is we have to, we're gonna ultimately go for the sum of the moments here around A, because that's what's gonna determine when this thing is balanced. Because I think there's too many unknowns to just do sum of forces. So let's go ahead and let's walk into this. Okay, so we need to solve for weight and we need to solve for buoyancy. Okay, so the weight equals, well, the weight of the object has nothing to do with the fluid. Okay, is the gamma of the wood, well, let's call it wood so it's not water, okay, times the volume of the wood, okay, has nothing to do with the water, okay, because it's a weight. The weight doesn't matter, okay? So the gamma of the wood is 0.6 times the gamma of water times the volume of the wood, okay? So I'm going to just kind of have that appear. Okay, so the weight is 529.74 newtons, okay? And then the more difficult one is the force of buoyancy, because the force of the buoyancy depends on how much of it is underwater, which is kind of the thing we're solving for. Is that really necessary? Sorry, somebody's starting an engine outside. All right, so the force of buoyancy has to do with the volume of the fluid displaced. So it is the gamma of the fluid, water in this case, times the volume displaced. Okay, so that is, well, the gamma of water, we know. Okay, so the gamma of water is 9810 newtons per meter cubed. Okay, times the volume displaced. And so what volume is underwater? Okay, so we're not worried about the portions that are not underwater, so it's this bit right here. Okay, so it has a length of L, and it is 0.15 meters by 0.15 meters. Okay, so we'll write that as 0.15 meters squared times L. Okay, so so we get that beauty, okay? And noting that L is what we want to solve for. Okay, now notice I can't do sum of forces at this point, because I have too many unknowns. I don't know AY, and I don't know L. So if I sum forces in the vertical, I'm not going to be able to solve it. And in the horizontal, well, AX isn't going to help us. So we're going to sum moments. Okay, and that's really unfortunate. Okay, but it's just the way it is sometimes. Okay, so I'm going to sum the moments around A needs to be equal to 0. Okay. So we're going to start, we really only have two forces, right? Because AX and AY go right through the fulcrum. So we have no forces there. So it's going to be FB. Okay, FB is going to cause a clockwise rotation. So it'll be negative FB. Okay, and we need its moment arm, or we need something to deal with this. So the way that I'm going to do with this is I'm going to say that its moment arm is like this. Okay, so this is its moment arm. Okay, but if I do that, then, okay, so noting that this is theta right here, then I note that not all of FB is in theta, so I need to kind of take the portion that's going this way. Okay, so I'm going to make FB cosine theta. Okay, and then the moment arm is going to be, well, let's see, it's the whole thing minus this bit right here, minus L over 2. Okay, so it's going to be 4 meters minus L over 2. Yachi machi, that's ugly, right? Okay. Now for the weight, we're kind of going to do it similar. Okay, the nice thing about the weight is the moment arm is easier, right? But only this portion of it is going at an angle, right? So it's going to be plus, now that's going to cause it to spin counterclockwise, so it's a plus sign, plus the weight times the cosine of theta, because only some of it is going, because I only need the portion that's going, perpendicular. And what else do we need? Well, we need the moment arm, which in this case is 2 meters. Okay, equals 0. Okay, so luckily, these cosine thetas are going to go away. Okay, I'm going to plug in for FB, because, they're in both terms. And I'm plug in for FB, and I get negative 220.73 newtons per meter. Okay, times L. Let's see, because that's from right there. Times 4 meters minus L on 2, plus the weight, which is 529.74 newtons, times the 2 meters, equals 0. Okay, so usually at this point what I'll do is I'll ask my class to kind of stare at this and see what they see. I'll simplify it a little bit, but you should already be looking at this and seeing what you should see to try to solve this, because this is not easy. But I'll go ahead and pause it and rearrange it, and you'll see the problem here. Okay, so doing just a little bit of algebra and keeping track of our units and things like that. So we've got newtons over meters right here, and I've got newtons per meter times meters squared, so that'll be newtons times meters, and right here, newtons times meters will give me newtons meters, okay? And what you should notice is that in L, which we're trying to solve for, we've got L to the first, L squared, and L to the 0 right here, okay, by not being there. Okay, so what this is a quadratic, okay? I would not expect you to be able to solve that on an in-class test. I guess it could happen on a quote-unquote real test or whatever, but on a test now because you guys have access to the internet, but I wouldn't go here probably. So you would use a solver. Okay, you could use your calculator or the internet or whatever that might be. If you did this, L equals 1.47 meters. Okay, or if you're really stuck, you could use quadratic formula. So L equals 1.47 meters. And so if we go back up to the little thing where I said this is how we're going to solve it, let's see if we can grab that little thing. We cannot isolate it. Okay, but we can zoom all the way in. Sine of theta equals 1 meter over 4 minus L. Okay. So if we go down here, I can say, well, the sine of theta equals 1 meter over 4 minus L. Okay, so if I plug that in, I'll say theta equals the inverse sine of 1 meter over 4 minus 1.477 meters. So theta equals, let's see here, 23.3 degrees. Okay, there's 8 minutes left, and I have one more example, but it's not really that important. So anyway, if anybody wants to see that one, just send me an email, and maybe I'll make a little video of it. But it's all about, I'll just kind of lay it out for you, but the idea is we've got a little surface like here, and there's an ice cube floating in it. And the question is, what does the surface do when the ice cube melts? Okay, does it go up? Does it go down? Does it stay the same? Et cetera, et cetera. And this has critical importance for global warming, right? Because one of the things that we talk about, or that a lot of people talk about, is they say, well, the ice caps are going to melt and there's sea level rise. And so one of the things that people think about is, okay, ice caps are melting, blah, blah, blah. But if you have an iceberg like this, and it melts, what happens to the sea? And you can do an experiment at home if you wanted to. I mean, I'll tell you the answer, but it'd be cool if you check it out. But the answer is that the water level will not rise. All of the sea level rise that they're projecting from global warming is because there's an ice cube sitting on the counter. Okay, these are the glaciers in the mountains, and they're melting. But the ones that are floating, okay, if you play with the math, and it's actually a little bit involved, you'll find that the surface will not rise. Okay, and I wouldn't ask you this one on a test because it's involved and it's too many symbols, and some of you guys are probably very comfortable with that, but not all of you. Anyway, have a good weekend. Be safe. There's a hurricane out there, or as I prefer to call it, a hurricane. So be safe, and I'll see you guys on the other side. So take it easy, and if you're watching the Saints game right now, I guess we'll good luck to the Saints and all that stuff. So be easy. All right, bye.